This is a reminder, Class Connect sessions are recorded and distributed for learning purposes that are listed here. As always, be respectful, appropriate, and participate, but please don't share personal information during the class for your own security reasons. We should be in the February 19th attendance ticket. I do need green checks. Let me know that you were able to open that. Want to make sure that everyone is able to follow along. Just have it open and ready to go. Remember, we do go over the answers in class. All right, so you don't need to do anything with it yet. Just have it open. Want to make sure everyone's got access to it. Again, link is in the chat box along with our password for today. Awesome. Okay, good. Seeing all those green checks. Remember, if you're having any issues with your attendance ticket, you can always let me know in the chat box. My general suggestion is save the password and then take pictures of the answers. Otherwise, you'll have to wait until the recording comes out later on in order to get those answers. But absolutely write down the password somewhere. Cool. All right, we are on day 15 of quarter 3. That means that we are a third of the way through the quarter. Kind of crazy to think about, right? So 15 out of 43, that's the same as 1/3. We did not have any school yesterday, so I hope you enjoyed your 3-day weekend. Today, though, we're going to finish up talking about Unit 4. So today we're going to talk about Pascal's and Bernoulli's principles as they relate to fluids. So you will have a short quiz today. And then we do have a game day tomorrow. Make sure you come tomorrow and participate in our Kahoot game. Remember, if you don't participate fully in the Kahoot game, you will have to complete the alternative assignment so that you can still get your points. So everybody gets points. It's just there's an easier way and a harder way. So make sure you come tomorrow. That way you can get your points in the easy way. And then Thursday, Friday, we will be beginning Unit 5. Unit 5 is actually kind of a long unit. It's also the unit that has our midterm exam. Midterm exam is coming up next week. Kind of a mind blower, right? So we do have a unit exam, a midterm exam coming up next week. So, but the nice thing is this week, no labs. Smiley faces if this makes sense to you. Looking at everything we've got coming up this week. Awesome. Looking good. All right. So there is a quick update that I wanted to give you. You'll probably notice this morning, some of you, that you did not have your normal Tuesday support session in the AM for you to get your extra credit. This is week 4. Yes, we are already in week 4 out of 10. So I just wanted to let you know that this is probably true across the board for many of you, but based on your current grades, as well as your STAR 360 math and reading scores, your schedule may have changed, right? So if you were passing all your classes and you did pretty well on math and reading, and then you might have gone to kind of a different level of how many classes that you need to attend. So if you're in the bronze group, you have Tuesday and Thursday in the AM for support, as well as Wednesday in the PM. If you're in the silver group, you have Monday, Wednesday, Friday, all in the PM. And then if you are gold, you only have Wednesday in the PM. Okay, so the way that you can figure out what does your schedule look like now, you can either go to your Class Connect schedule or the Plan tab. And the Plan tab does show you when all of your support sessions are. That being said, I will probably put an announcement up later this afternoon just to let you know which group you're in and to kind of let you know what your schedule is going to look like from now on in the announcement, just to make it super, super clear. Okay, thumbs up if this makes sense, everyone. Okay, I mean, they're all still optional sessions and they're all, there's still opportunities for extra credit. So my class, it doesn't have a huge effect on you, but remember that in math and in English, whether or not you have required classes, so this really affects whether or not you have more required classes. That's what's really important. So definitely make sure you double check your English and math classes for this week. All right, awesome, everyone. So we are talking about fluid forces. We've been taking a look at what pressure is for fluids. We also talked a little bit about density, talked about buoyancy. Today we're going to talk about 2 really important principles with fluids, Pascal's principle and Bernoulli's principle. So today we should be able to understand how Pascal's principle is related to hydraulics, and then we should also be able to explain the relationship between fluids and flight, fluids and airplanes, how they fly. Okay, so today we're going to go over how do airplanes fly. Exciting topic. All right, in case you didn't know how airplanes fly. So let's go ahead and first jump into Pascal's principle. So Pascal's principle, this is Blaise Pascal right here. He was a 17th century French scientist, so that means he's from the 1600s, right? So quite old. But what Pascal said is that pressure in a confined fluid, so for example, in a closed bottle, is going to be the same throughout the fluid, okay? Which means that if you try to increase pressure at any point in that fluid, okay, like with a piston, it's going to result in a uniform increase in pressure at all points of the fluid. Okay, so this should make sense. If you take a water bottle, a plastic water bottle, and you squeeze it really hard in the middle, does the entire bottle get hard, or do different parts of the bottle get hard? Tell me in the chat box. Think about the top of the bottle versus the bottom of the bottle. If you squeeze in the middle, do the top and the bottom both get hard? Tell me in the chat box. Do they both experience that increase in pressure? Awesome. Got an answer from Ireland. Got an answer from Caleb. Dorian. Yes, exactly. So you actually have experienced this all the time, right? You squeeze in the middle, and yet every single part of the bottle experiences more pressure. So wherever you add pressure, it doesn't matter. The entire confined fluid is going to have a uniform, meaning the same increase in every other point of the fluid. Okay, so let me go ahead. We're going to do a demo of this, just because I know that's a little bit hard to wrap our brains around. So let me go ahead and push this up on the board. Awesome. Thumbs up here if you can see my screen. Okay, perfect. I did want to let you know that my daughter was super sick over the weekend, so I'm not as up to grading as I should be. But I do have about half of the labs graded, and I'll make sure I finish the rest of the labs today. Okay, so just keep that in mind. If you have submitted your lab report, I haven't forgotten about you. I just need to finish grading them, okay? But there are about half of them graded. Cool. All right, so I'm going to go over to our Unit 4. And I don't know if you guys were aware of this, but there are some at the bottom of each of your units. There are some additional reading materials that you can always take a look at. All right, so I'm going to go down to the additional reading materials and look at Pascal's principle, because they have a really good demo in there for today. Number 5. Okay, so you should be able to see this here. So what you can see here is that you can see at the top that we have a main piston, and you can see that you have much smaller pistons throughout the fluid at different parts. Okay, so what we're going to see is we're going to see what happens when we push on the main piston to all the other points of the fluid. All right, so let's go ahead. I'm going to press play. Take a look at that. So we're putting a 5-gram mass on the main piston. It's going down. See what happens to the side pistons. Looking good. Removing those. See what happens to those side pistons. Awesome. All right, so what I'm going to do, I'm going to go ahead and restart this really quick. And then I want you to go ahead and take a look at what happens at some different points here. Okay, so as we added these different masses here, tell me what was happening to the smaller pistons. Were they moving out at the same rate as each other or at different rates from each other? Go ahead, tell me in the chat box. These smaller pistons, did they move out the same amount as each other or different amounts from each other? So take a look. This moved out, what, like 1 centimeter? This moved out like 1 centimeter. This moved out. Don't just say the same thing as the person above you. Take a look at our actual pistons here. Take a look at our actual pistons here. Look at the amounts that they went out. Measure how much the top went out. Measure how much the bottom went out. Measure how much this top one went out. Measure how much this bottom one went out. Yeah, they all went out by the same amount, okay? It didn't matter. Yeah, they are all the same. It should look all the same to you. It should not look different, all right? So what you should see is that as we added more weight, or as we took weight away, no matter what, the small pistons always did the exact same thing. Smiley faces if that makes sense. No matter where the small pistons were, they all did the exact same thing. They all looked exactly the same. And that just goes to show you that regardless of where you're adding pressure, right, we added pressure up here at the top, regardless of where you're adding pressure, it doesn't change what's happening in the rest of the fluid, right? The pressure change at the top is the same as the pressure change at the bottom because the pistons all did the exact same thing, okay? So hopefully that should start making a little bit more sense. All right, awesome. So go ahead. This is number 1 in your ticket. Give me a green check when you have it saved. Your first blank is going to be the word same, and your second blank is going to be the word uniform. Go ahead, fill those out. You have 40 seconds to give me a green check and get that done. Go, go, go. All right, need some more green checks letting me know that you have filled in those 2 blanks. From Andrea, Tony, Ashton, Bradley, Dorian, Dree, Dylan, Edwin, Hope, Josiah, Justin, Matt, Maxine, Mike, Miguel, Misael, Nate, Razi, Suji, and Yusra. Green checks for number 1. Oh, it's okay. Green checks for number 1. Let me know that you're all set. Oh yeah, for sure. Sorry, Misael. There we go. Awesome. Looking good. All right, let's go ahead and move on, everyone. All right, let's go ahead and keep on moving here. So here's the important part of Pascal's principle. So Pascal's principle is used in hydraulic machines. So how many of you have ever seen those kind of pumps that are used in order to lift cars up? Okay, if you even at home, there's like small hydraulic machines that you can use in order to lift a car up, right? You pump it a whole bunch. Yeah, exactly. So those are hydraulic machines, and they're super useful because all you have to do is you have to pump it a bunch of times, and magically you are able, yes, exactly, a jack. I knew I couldn't remember what the word was. Thank you, Tariq. So when you use a jack, the amazing thing is that you use these small movements to pump up the jack, and yet somehow you are magically able to lift a car. Okay, that should blow your mind because in real life, you are unable to lift a car, right? Without a jack, you would not be able to just lift the car up using your own strength unless you're like I don't know, the Hulk, right? So, but in real life, that's not possible. So what we use is we use a hydraulic jack, and a hydraulic jack allows us to use very little effort several times in order to lift a car, okay? So hydraulic machines use this idea of uniform pressure in order to multiply force, in order to make it so that we can lift really, really, really heavy things. Okay, so this is using Pascal's principle. So remember, all the molecules in a fluid are going to respond to a pressure change at the same time. So if you push on one part of the fluid, that's going to transfer force to all the other parts of the fluid. Okay, so let's take a look here. Imagine that we have a bunch of different points of our fluid here. So I'm going to go ahead and draw these, right? So we have one point of fluid right here, and then we have 1, 2, 3, 4, 5, 6 points of fluid over here. Okay, smiley faces if you're following along with me so far. So far we've got just a single point of fluid here, and then about 6 points of fluid over here. Cool. All right, so what's going to happen is we're going to push down on this little point of fluid right here, okay, which is going to apply some force, all right, some pressure to this area right here. Okay, so we're going to apply some pressure right here. Okay, but remember, Pascal's principle says that that means that every single other point of fluid also feels the same change in pressure. Okay, so they're feeling the same change in pressure. So for every single point over here, right, they're feeling the same change in pressure. But take a look at this now. Misael, you can go back to it in the video, or if we end early, I can go back to it then, right? But I don't want people to put answers into the chat box because that doesn't allow you to actually see what you missed, right? So we'll go back to it at the end, or you can watch the video, okay? Thank you, Misael. All right, so take a look over here, though. So I pushed down on one part of the fluid, but over here, all 6 parts of these fluid actually feel that same change in pressure. But if you take all those different points and put them all together, that means that there's a really, really big change in force here. Smiley faces if that makes sense. So you take just one little force over here, and over here, that force gets multiplied by 6, right? Which means it's a much greater force. So even though we add only a little bit of force here, like with a jack, you're only adding a little bit of force right here, the car feels that force spread across many different parts of the fluid, and so you're able to lift a car. Okay? Thumbs up if that's starting to make more sense. Thumbs up if that's starting to make more sense. Again, on a small part, we add a small force, but on a big part, it experiences a big force. Cool. All right, so let's take a look at a little bit of the math here. So again, Pascal's principle says that pressure is going to be the same everywhere in the diagram. So the pressure that we apply to one side, okay, over here, the easy side, P1, is going to be the same pressure as we add over here to the car, P2. Okay, but remember, we learned an equation for pressure, and the equation for pressure is force divided by area. Okay, so if we say that the two pressures are equal, then we can also say that the force divided by areas are also equal. Smiley faces if that makes sense. All right, so I just substituted pressure equals force divided by area. I just substituted that here. Okay, so I'm just doing a substitution here. Okay, it's the same equation. Okay, so the force of one side divided by the area of one side should, in theory, right, if this is done correctly, equal the force of the second area divided by, equal the force of the second side divided by the area of the second side. So let's go ahead and actually figure out what this looks like. All right, so over here, what we're trying to figure out is we are trying to figure out the force that we need to apply on side 1. Okay, so F1 is what we're trying to figure out. Okay, but we do actually know all the other information here. So we actually know the area of side 1. We know the force of side 2. Weight is the same thing as force due to gravity, right? So we know the force due to gravity of the car. Hi, Andres. And we also know the area of the second side as well. So let's go ahead and start plugging this in. Okay, so force is going to be F1, right? We don't know it yet. Divided by the area of side 1, which is 2 meters squared, equals, on the other side, the force of the car, which is 2,000 newtons, divided by the area of the car, which is going to be 100 meters squared. Give me a thumbs up if it's making sense where I'm getting these numbers from. Again, the data on the left comes from the side 1 over here. The data on the right comes from side 2 over here, the car side. Okay, so our side, car side. Okay, so now all we need to do is we need to do a little bit of math. Okay, so what we want to do is first, can we divide a letter, a variable, by a number? Can we divide a variable by a number? Can I do anything on the left side yet? Can we divide a variable by a number? Tell me in the chat box. You can divide a letter by a number? Chat box. No. So we can't do anything with this yet. So we're going to go ahead and just keep that the same. So we're going to say F1 divided by 2. And I'm going to go ahead and just drop the units for now just to make it easier to see. Now on the right side though, can we divide 2,000 by 100? Can we divide 2,000 by 100? What does that equal? Right? We couldn't do a variable divided by a number. That's not possible yet. But 2,000 divided by 100, what does that equal? It does not equal 200. Try again. Go ahead, use your calculator. Use your calculator either on your phone or on your calculator. What is 2,000 divided by 100? There we go. There you go. Yes, it equals 20. All right, so 2,000 divided by 100 equals 20. Awesome, so that was good. So now the last thing we need to do is we still need to get this force by itself. So remember, algebra has us do the opposite equation, the opposite function in order to get things by themselves. So if we want to get the force by itself, we need to do the opposite of dividing by 2. And what's the opposite of dividing by 2? What is the inverse function, the opposite function of dividing by 2? No worries, Alyssa. Yeah, we need to multiply. So we're going to multiply by 2. But whatever I do to one side, I also need to do where? Algebra tells us that whatever we do to one side, we also need to do where? Yep, we also absolutely have to do it to the other side. Okay? So what happens on this side is when you do the opposite function, remember it cancels out, so we get rid of it. So now we're just left with our force, F1, which is exactly what we wanted. And on the other side, what is 20 times 2? What is 20 times 2? Okay, we have some numbers being multiplied. We can definitely do that. What does 20 times 2 equal? Yep, it equals 40, and this is a force, so what should my units be for this force? What's our units for force? So let's go ahead and add back in our units now that we're to our answer. Newtons. Remember all of Newton's laws have to do with forces, so this is actually 40 newtons. Okay, so what I want you to take a look at over here is we're going to compare these. Okay, so for the side 1, okay, we had a small area, okay, compared to the big area over on the right. And what about the force? Is the force smaller or larger than what's on the right? Tell me on the left, is this 40 newtons smaller or larger than the weight of the car on the right? Tell me in the chat box. Yeah, it's definitely significantly smaller, right? So we have a small area, and therefore we also have a small input force. Where on the other side, we had a big area, and we had a big output force. Okay, so which side is easier? The side with the small area, small force, or the side with the car with the big area and big force? Tell me in the chat box, which one is going to be easier? The small area, small force, or the big area, big force? Think about applying a force. Which one's going to be easier? The small side or the big side? Applying a force of 40 newtons versus applying a force of 2,000. Yeah, definitely the small side. So the small side is actually significantly easier. Okay, whereas the car side, that should make sense. The car side is much harder to do, which is why we can't just lift a car by itself. Okay, so smiley faces if this is beginning to make sense. By using a small area on one side, with just a small point of pressure, that multiplies all the forces on the other side where there are many points of pressure. Okay, so you can be on the small side with the small force, which is very easy, pumping, 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 in order to, on the other side, where there's a big area and a big force, in order to lift a car. All right, so this is the magic of physics, that on one side, by using Pascal's principle, it's super easy. On the other side, it's super hard. Okay, thumbs up if you better understand that now. Thumbs up if you better understand that now. Okay, so Pascal's principle, one side is easier than the other side, based on how those pressures are distributed. Awesome, so I'm going to go ahead and show you a quick video of this, just because I want to make sure you kind of see it in real life. So let me go ahead and grab. All right, it's about 1 minute, so make sure you give me a green check when you finish watching it. Go, go, go.
One way to demonstrate this is to use a simple system of 2 syringes, tubing and water. When we apply pressure to push one syringe down, the other syringe goes up. Because the fluid is incompressible, the pressure is transmitted from the first syringe to the second syringe, causing it to fill with water. If you'd notice, it is a lot more difficult to push the larger syringe down. Due to Pascal's principle, the pressure that the fluid experiences at each point in the system is equal. Therefore, the pressure at each syringe is equal. We also know that pressure equals force divided by area, so mathematically, each pressure can be replaced by its respective force over its area. The smaller syringe has a much smaller area, therefore it requires less force to achieve the same pressure.
All right, green checks if you finished watching it. Awesome. So I don't know why there was a super robotic voice for that. Interesting way to make your video. But anyways, what I wanted you to notice is the voice said that one side was harder. Which side was harder, the big syringe or the small syringe? Tell me in the chat box, which side was harder, the big syringe or the small syringe? Yes, the big syringe. Exactly. So the big syringe is like trying to lift up a car by itself. A big area with a big force. It's much, much, much harder. On the other side, though, he was able to use a small syringe, right, with a small area, and that one was much easier. It required less force in order to push it. Okay, so smiley faces if that makes a little bit more sense now that you've actually seen it in action. Okay, so I'm trying to show it to you in many different ways because I know it's kind of a mind-blowing topic. Awesome, cool. All right, looking good, guys. So what I just want to remind you guys is what is the equation for pressure. Go ahead, use your polling tools. Sorry, wrong polling tools. Use your polling tools. What is the equation for pressure? Distance per unit time, force per unit area, or work per unit time, right? I said pressure equals what? That's where we got that second equation from. No worries, Michaela. Let me go ahead and get you your ticket for today if you didn't get it already. Looking good. All right, get your polling answers in there. What is the other equation for pressure? Yes, absolutely. Looks like we are all saying letter B, and that is true. That is going to be force per unit area. This is actually number 2 in your ticket. Go ahead and use your, go ahead and take 30 seconds to answer number 2 in your ticket. Give me a green check when you have it saved. Go, go, go. Yeah, Andres, we did. If you missed it, you can see it in the video once that's uploaded in the recording, or if I have time at the end of class, I can go ahead and go back to it for you. All right, just a reminder, everyone, please make sure you don't put any answers in the chat box just because I want kids to actually be able to see what they missed. Yes, thank you, Andres. All right, 10 seconds, everyone. Green checks. All right, looking good. Waiting on a green check from Amir, Andrea, Ashton, Bradley, Dorian, Dree, Dylan, Edwin, Josiah, Matt, Maxine, Miguel, Misael, Blossom, and Yusra. Green checks for number 2. Remember, if you're having any issues, just write down the password and take a picture. Otherwise, you'll have to wait until the recording gets uploaded later. Awesome. All right, let's keep on going. So last thing that we need to talk about today is Bernoulli's principle. So Pascal's principle is all about hydraulics. Bernoulli's principle is all about flight. Okay, so here's the thing. How many of you have heard of this idea of aerodynamics, right? Think about a car. The more aerodynamic it is, what does that mean for the car? Tell me in the chat box. Or for a jet, the more aerodynamic it is, what does that mean? Yes, it goes faster. It cuts through the air much easier. Exactly. So remember that air, even though we can't see air, there is still air, and air is made of atoms. Okay, it has particles. So even though we can't see it, it's still affecting us. Okay, and it might affect us not very much until we start trying to go super, super fast. Right, so aerodynamic design is the idea. Yeah, she's super sick, Andres. So aerodynamic design is this idea of, as you try to fly through a fluid like air, we want to reduce friction as much as possible in order to move as fast as possible. Smiley faces if that makes sense. If we can reduce the amount that air affects a plane or affects a car or affects a shark, like the way water affects a shark, you can go faster, okay? Yeah, I know. She definitely sounds very gross right now. Poor baby. All right, so the way that we can do these, there's many different ways, but a couple ways are, for example, having a smoother shape, right? So the smoother, for example, a shark has super smooth skin that allows them to cut through the water better. Or, for example, what do you notice about the noses of both of these things? Of your airplane, of your shark, of your helmet? What do you notice about the noses? The noses. Tell me in the chat box. What are some observations? Are you teaching too? Yeah, exactly. So they kind of come to a point, kind of like a rounded point, but a point nonetheless, right? So these are what we call like raindrop shapes. So a raindrop shape is going to cut through the air or through the water much better. Okay? So what? Yeah, aerodynamic or water dynamic, exactly. So what this idea of friction, of resistance to moving through a fluid, this is what's called drag, right? So literally when you think about like, oh, they're dragging you down, right? Think about the same thing in terms of aerodynamics. Drag is what's keeping you from going as fast. So the way that things move is this relationship between drag and their aerodynamics. Okay, so drag's trying to slow you down. Having better aerodynamics helps you to go faster. Okay, so now let's talk about how do airplanes, okay, overcome this idea of drag. How do airplanes actually work in order to fly? Okay, so this is Bernoulli's principle. So Bernoulli's principle says that air particles on top of a curve, like you can see here, okay, air particles on top of a curved wing need more velocity to get around that curve. Okay, so in order for them to get over the top of this wing at the same time as the ones on the bottom, they have to go a much further distance. So they have to speed up to go much, much faster. And as those particles speed up, they're going to spread out. And if they spread out, are there more or less collisions? Tell me in the chat box. If particles are spread out, are there more or less collisions? Spread out. The more spread out particles or people are, right? Think about if you're more spread out from other people, are you going to have more or less collisions? Less. We're going to have less collisions, right? So we're going to have less collisions, which actually means lower pressure. Okay, remember, we said pressure and collisions are the same thing. So if we have less collisions, that means there's lower pressure above the wing. Smiley faces if that makes sense. So above a curve, they have to move faster, they spread out, there's less collisions, you actually end up with lower pressure. Michaela, we have not yet done number 3. You would see it on the board. All right, don't worry, don't worry. I'll let you know when we get there. Now, on the bottom, on the other hand, those air particles don't have to move as fast, right? So these ones are slower, okay? They're closer together, and if you're closer together, what happens to your collisions, more or less? If you're slower, you're closer together, what's happening to your collisions? Yeah, those particles, since they're so close to each other, they end up with colliding a lot more. So more collisions means we have a much higher pressure. So higher pressure. Okay, smiley faces if that makes sense. So above, they're moving fast, lower pressure. On the bottom, they're moving slow, higher pressure. Okay? Awesome. Now, what this leads to is I'm going to go ahead and show you this demo. So this is just a strip of paper. And what I'm going to do, you can actually do this at home when you have a strip of paper, is you can actually blow on top of a piece of paper and see what happens. All right, so I'm going to go ahead and blow on top of this. So as I blow on top of that paper, what's happening to the paper? So I'm blowing on the surface of it, not the bottom of it. I'm blowing on top. What starts happening to that paper? Tell me in the chat box. Yes, it goes up. So that should really blow your mind because what you're probably thinking is that you would need to blow under something in order to get it to go up. But in reality, in order to get something to go up in air, you can blow on top of it. And because there's less pressure on top, that suddenly makes it want to go up. Smiley faces if that makes sense. All right, I'm going to go ahead and show you what that looks like. Okay, yeah, it starts to go up. So as you blow on top of the strip of paper, you can see here, that creates less pressure, right? We increase the velocity of air, decreasing the pressure on top. On the bottom, right, the air is still, it's not moving, and so the bottom pressure is much higher because it's not moving and the molecules are super close together. So the result is what we call lift, all right? So low pressure on the top, high pressure on the bottom means that overall we end up with more pressure going upwards or more force going upwards, and this results in lift. So take a look here. We decrease the force on top pushing down, and the force on the bottom is much higher pushing up. So overall, the overall net force is up. And this allows planes to fly. Smiley faces if you understand. This allows planes to fly. Okay. So the wings shape is what makes planes fly, right? So the curve on top means that we have faster moving air and very little pressure pushing down. On the bottom, we have slower air, which means a lot of pressure pushing up. Okay, and so the overall result is lift. The overall net force, the total force, ends up still being upwards, allowing the wing to go up, allowing it to fly. All right, go ahead, match these up. Let me know that these make sense. All right, remember, increased velocity, think about what's happening to the particles and therefore the pressure. All right, decreased velocity, think about what's happening to the space of the particles and therefore the pressure. Yeah, right, Tariq? It's a giant metal bus with wings. Looking good. Go ahead, get your answers up there. Use any color but red. Please use thin lines to make it neat, to keep it neat. Go ahead, everyone. Go, go, go. Get your answers up there. Awesome. I see Dorian, Martina on the board, Amanda on the board. Looking good. Thank you for your participation. Rosie's on the board. Tony's on the board. Arrow and Miguel, thank you. Mike is on the board. Awesome. All right, so many names. I'm having a hard time keeping up. Awesome. Caleb, thank you. Looking good. All right, let's go ahead. I'm going to pause your tools. This is going to be the answer to number 3 in your ticket, so get that ready to go. Sorry, I'm just going to shrink this a little bit. Here we go. Awesome. All right, so drag. Yes, drag is frictional resistance, right? Dragging you back, keeping you from moving as fast. Lift is because there's a net force pushing upwards because of faster air over the top of a wing. Increased velocity means particles spread out, so they actually end up with less air pressure. And decreased velocity means that particles are closer together, resulting in more air pressure. This is number 3 in your ticket. Give me a green check when you have it saved. You have 45 seconds. Ready, set, go. All right, waiting on a few more green checks. Amanda, Amir, Ashton, Bradley, Dree, Dylan, Edwin, Ireland, Josiah, Justin, Maxine, Michaela, Misael, Blossom, Suji, green checks. Just want to make sure I'm not leaving anyone behind. Looking good. We're almost done here, everyone. Green checks, green checks. Looking good. All right, everyone. So here was our objective for today. We talked about Pascal's and hydraulics. We talked about Bernoulli's and flight. Here is your quiz for today. Remember, all the answers you just did in your attendance ticket are actually the information you need to get 100% on your quiz. So do your quiz right next to your attendance ticket, have them open at the same time, and then submit them at the same time. Should only take you maybe 5 minutes. It's a super short quiz. All right. Give me a thumbs up if you feel good about today. Thumbs down if you're confused about anything. Just want to check in again really quick. Awesome, looking good, seeing lots of thumbs up. Love it, love it, love it. Cool. All right, everyone, here's your last word. Have a wonderful day, and I will see you later. Bye, everyone. If you missed anything, it will be in the recording. I'm sorry, I do need to go to my next class, so if you missed anything, just wait for the recording. It'll be up at 2 o'clock, and make sure you have the password for today saved so that you can get back into it, all right? Go ahead, go, 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 everyone. Got to go to my next class. I will see you all later. I'll put anything on the board in case you missed it.